Language models are powerful, but their knowledge is finite. Every fact they know is frozen at the moment their training ended, leaving them unable to account for anything that happened yesterday. They are also blind to private information. Your company's internal SOPs, latest product prices, or updated HR policies are invisible to a model that only knows what was available on the public internet years ago. When these models hit a knowledge gap, they are prone to hallucination. Instead of admitting they lack the information, they often generate plausible-sounding but entirely invented facts to fill the silence. Retrieval-Augmented Generation, or RAG, was engineered to solve this. It follows a three-step sequence. First, it retrieves relevant data from your own documents. Second, it augments the prompt with that information. And third, it generates an answer based on that evidence. This creates a clear division of labor. Use RAG when the system needs to access specific, changing facts. Safe fine-tuning for when you need to adjust the model's personality, tone, or specific formatting habits. Think of RAG as a researcher for the AI. It forces the system to consult a specific set of relevant documents before it is allowed to formulate a response. To make this work, raw data has to be processed. A language model simply cannot ingest a massive PDF or a complex JSON catalog in one single piece. We handle this by chunking data, splitting documents into small, manageable pieces of roughly 500 to 1,000 tokens. This size is a deliberate balance. It's large enough to keep the context intact, but small enough to filter out irrelevant noise. Chunks are converted into embeddings, strings of numbers that calculate relationships. Because this math captures intent, phrases like airplane noise block and active noise cancellation converge tightly together in a 3D grid, despite sharing no exact words. Chunking and embedding turn your unstructured documents into a searchable map, where the proximity of 2 points represents how closely related their ideas are. This map is the key to answering questions. When a user asks something, that query is instantly converted into its own embedding and placed into the same mathematical space. Using cosine similarity, the system measures the angle between the user's query and stored document chunks. Production systems use hybrid search. A secondary scanning layer ensures it also locks onto exact alphanumeric identifiers, like product SKUs or error codes. This combination ensures the AI focuses only on a tiny, high-quality subset of your data, rather than trying to search its entire memory at once. Once the right chunks are found, they enter the prompt construction phase. These pieces of evidence are injected into a dedicated section of the prompt, separated from the user's question. The system then issues a strict instruction. The model must answer using only the provided context. This effectively prevents the AI from relying on its own internal, outdated memory. For safety, we include a fallback rule. If the retrieved documents don't contain the information needed for an answer, the model is instructed to state that it doesn't know, rather than attempting to guess. This structure forces the AI to behave as a reading comprehension tool. It significantly limits the model's ability to wander off topic or fabricate information by anchoring every sentence to the provided text. Building the pipeline is only the first step. Without a way to measure performance, a RAG system can fail by retrieving the wrong context or ignoring the evidence it was given. This is where we measure faithfulness. By comparing the AI's answer directly to the retrieved chunks, we can verify that every claim the model makes is actually supported by the source text. We supplement this with metrics like answer relevancy and context precision. These automated checks act as a quality control layer, ensuring the system retrieves the right information and uses it to answer the user's question directly. The strength of this system is directly tied to the quality of the documents you provide. When the data is clean and the retrieval is precise, the AI stops being a closed box and becomes a tool where every answer is tied to a specific, citable source. General-purpose language models are built to guess the next word. To turn that chaotic probability engine into a reliable, domain-aware assistant, you have to anchor it to a rigid architecture. Many developers assume that if an AI gives a bad answer, you fix it by writing a more clever prompt. That is a misunderstanding of the technology. Ask an ungrounded model for the best headphones to block airplane noise, and it will recite generic marketing copy from its training weights. Ask a grounded system, and it cites specific test results directly from your internal product catalog. The most advanced language model in the world will fail if you do not fetch the relevant context before generation begins. Ultimately, everything relies on the retrieval pipeline. We are going to build a complete product assistant from scratch, using the Gemini API to map semantic meaning. Once the system is running, we will construct an automated LLM as judge evaluation loop and a systematic debugging workflow to measure its accuracy. Because building a production AI system is an exercise in rigid data retrieval and telemetry, not creative writing. Everything starts with the data. We take raw JSON files, product names, categories, features, and parse them into clean, manageable text components. We split that text into blocks of 500 to 1,000 tokens. If too large, retrieval is noisy. If too small, context is lost. By mathematically overlapping the boundaries, we ensure specific paragraphs and sentence structures survive the split intact. But machines do not read text. To search these chunks, we must translate their semantic meaning into numbers. The Gemini embedding model reads each chunk of text and converts it into an exact 768-dimensional vector representation. This visualization maps those vectors. To measure how close in meaning two chunks of text are, we calculate the spatial distance between them using a formula called cosine similarity. Notice the specific distances between headphones, earbuds, and laptops. When a user submits a query for blocking airplane noise, that request becomes its own new coordinate in the same space. Even if the user didn't type the exact phrase active noise cancellation, the system identifies the semantic overlap. The mathematical distance between the query and headphones is incredibly short, while laptops remains far away. This spatial relationship means semantic search naturally maps human intent, bypassing the limitations of exact keyword matching. With the vector index built, we move to the retriever module, where the user's query actually interfaces with the stored data. This search function relies on strict filtering. We apply a minimum similarity threshold. The system identifies a few highly relevant matches and immediately blocks the rest. If you bypass this filter and dump hundreds of retrieved chunks into the prompt at once, you trigger a state called context overflow. The sheer volume of text paralyzes the model's attention mechanism, causing it to ignore critical facts. The engineering fix is rigid limitation. We restrict the top K retrieval parameter, isolating exactly 3 to 5 chunks, and prioritizing only the absolute highest similarity scores. Those surviving top chunks are then injected into the final prompt for the language model. We wrap that retrieved context in a rigid instruction boundary. The prompt explicitly orders the model: answer using only the context below. Do not use external knowledge. To prove this boundary holds, we run an unanswerable question test. We query our product catalog about the local weather. Because the retrieved product chunks contain zero meteorological data, the strict prompt forces the model to reply, "I don't have information in the provided context." A disciplined retrieval-augmented generation architecture prioritizes verifiable refusal over hallucinated guessing. Standard latency and error metrics are useful, but they cannot measure the factual accuracy or clarity of a generated paragraph. This schematic shows the LLM as judge framework. We feed the original source chunk and the final generated answer into a separate, highly constrained evaluator model to grade the qualitative traits programmatically. You must configure this judge model to run at temperature 0. We need mathematically consistent grading, not creative variation. This dashboard tracks 3 specific vectors. Faithfulness checks if the answer is supported entirely by the text. Context precision verifies the relevance of the chunks. And context recall ensures the system retrieved all the necessary information. These automated grades form the basis of our regression tests, the structural safety net for the entire pipeline. Without regression testing, a minor optimization like adjusting chunk size can cause a chain reaction that silently breaks dozens of previously correct answers. By hard-coding expected keywords and specific source IDs into our test suite, we lock in the accuracy of the system against future code updates. Without automated deterministic evaluation, a pipeline degrades silently. Continuous telemetry is a non-negotiable requirement for production. Eventually, the pipeline will fail. A user will ask a valid question, and the assistant will output a highly confident, completely incorrect answer. When this happens, follow the first rule of systematic debugging. Do not immediately blame the language model. Isolate the failure by working backward. Trace the error from the generated output, back through the prompt, to the similarity scores, to the retrieved chunks, and finally to the user's initial query. First, print the retrieved chunks to the console before generation. If they lack the correct facts, it's a retrieval failure. Fix this by adjusting metadata filters or lowering the similarity threshold to catch the missing context. But if the printed chunks contain the correct facts and the final output is still wrong, you have a true hallucination. You fix this by enforcing stricter prompt rules and lowering the generation temperature. Professional debugging requires treating these errors as traceable data pipeline faults rather than unpredictable AI mysteries. We do not ask a general-purpose model to remember everything from its massive training dataset. We provide it with exact facts at runtime. We force it to stay grounded to those specific facts, and we continuously measure its output. That is the architecture of a reliable knowledge system. You prepare the documents, calculate the embeddings, search the vector store, retrieve the exact context, constrain the prompt, generate the answer, and evaluate the result. Rigorous data engineering is the only mechanism that transforms an unpredictable generative model into a trusted, enterprise-grade tool.